Hi everyone, welcome back to Becoming a ROS Developer here at The Construct. My name is Rodrigo, and as always, today we have a student from our ROS Basics in 5 days, and this is for C++. His name is CJ, and he's going to be showing us how he did the project for this course. So you take a course, and then at the end to prove your knowledge and to do um, to make sure you got everything from the course, we do a little project that interacts with a real robot here. So he's going to be showing us how he solved this project that involves using topics, services, and actions. Hi CJ, how are you?
Good. How are you? Nice
I
to meet you finally.
I am good too. Nice to meet you too. So the floor is yours. So whenever you want to start sharing your screen and explaining what your project is about, you can go ahead and do it.
Okay. Let me first share the screen. So can you see my screen right now?
Yes, we can see it.
Yeah. Okay. Yeah. So my presentation for the final project is divided into four parts. First, I will show you a video of me testing my code in a real condition, and then in the following three sections, I will just disclose some details of my algorithm, how I design the service, and how I design the action. So as first part, let me share this video. As you can see here on the left side, we have the terminal showing what's going on and what are the comments that I was using. On the right-hand side is how the robots is running in the real robot lab. Um, so yeah, first you see I was trying to load my launch file. So now I'm loading the IDE in a different window. It takes some time to load. As you can see, the package name is called the wall follow. And in the launch folder, I just have a one launch file there. It's kind of hard to control it. Yeah, wall follow node dot launch.
Okay, I see.
Yeah, then I just use this one launch to launch the service and launch the action server.
Okay.
Mm-hmm.
And yeah,
And
while
also,
it's starting to move,
yeah,
can you explain us, what it's doing a little bit?
yeah, sure.
Not too in
It should
depth.
be pretty clear though.
Okay,
As
okay.
you can, yeah, as you can see, first, what I'm doing right now is rotating the robot and and measuring the distance from the um, distance from the front wall to the robot and the minimum distance from the any kind of wall to the robot. So you can see as you rotate the robot, those values are keep changing until the two distance are pretty close to each other. In this case, it's only 0.02 meter difference between the middle distance and the minimum distance, which means that the minimum distance is actually very close to the front of the robot. So now I will just move forward. As you can see here, I'm showing the information called the move forward till the front distance is less than 0.3. So that's how the service works. And then once the robot has its distance from the nearest wall less than 0.3 meter, then I will rotate the robot again until the nearest the minimum distance is at its
Right side.
left front. Yeah.
Okay.
So right now it's
rotating
it's
now.
rotating. Yeah, rotating to make sure that the nearest distance is at its left front.
And at
Not
this
not
point, the service is still running, right? Okay, I think
Yeah.
it just ended because it
Yeah,
found
it ended.
Okay.
Yeah. So what this three information tells you that it tells you that because the range array has like 720 elements,
Yeah.
and you're supposed to get the minimum distance at its 270th um, element.
Yeah.
So so this three information is telling you that distance at the range 270 is 0.22, and the current minimum distance is at 276 element. So which means that actually the orientation of the robot is pretty close to what I want it to be.
Right.
So
Not
that's
exact,
how
close enough.
Yeah, it's not exactly 270, but it's very close. It's like only 6 elements away from what I want it to be. I set a threshold like 8 element tolerance in my code, so that it doesn't take too much time to actually find the minimum, to find the optimum position.
So let me ask you, if you weren't adding this threshold, then it would take longer, or what will happen?
It actually shortened the time
Okay.
of this service to find the minimum, or to find the optimum orientation of the robot.
Right.
Yeah.
So now it's quicker. Yeah.
Yeah. So now it tells me, okay, now we're found. We're good to go. We are finishing the service here, and now we are starting the wall following motion. Now, what I'm doing here in the video is I'm trying to subscribing to 2 different topics that would tells me the feedback and the final results from my action server. So as you can see here, I have a server name called Record Autumn, and it has like 5 channels, and I will listen to this Record Autumn feedback and the Record Autumn result. So you will see that at the beginning, there will be nothing showing from the result channel. And once the first lap is done, and all the points that the robot just passed by will showing will be getting from the result channel.
Okay.
Yeah. So what you're seeing now is I'm trying to echo
the feedback of the action.
The feedback information. Yeah. So you see in this feedback, each bit of information has a current distance at the end here. It basically tells you how long the robot has been moving.
Okay.
Now I'm listening to result
for the lab to complete.
Yeah, the result isn't showing anything because the first lab isn't finished yet.
Right. And how did you make it? Well,
yeah,
I guess
so
you'll explain a little bit later.
Yeah. So the way I decide whether first lab is finished is this. It has to satisfy 2 conditions to judge whether the first lab is finished. The first one is the robot has to move more than 7 meters, and
more
then
than 7, okay.
Yeah, more than 7 meters. And then the second condition is the latest point that this robot passed by has its minimum distance to old. Well, let me see, because I'm recording all the points that this robot passed by. So I will I will calculate the distance from the latest point to all the older points. Right, so if I found that this latest points is very close to any one of those older points, and these 2 points, and as of now, the robot has moved more than 7 meters, then I call it the first lap.
Right.
Yeah.
Okay, so you're comparing both those two things, and if they're satisfied, then the action
Yeah,
returns.
the action stops. The results actually it gives me the final array
Right.
of the points. Yeah.
And do you make it so the robot stops, or does it keep going?
Yeah, I think now it's stopped, and you
Okay.
can see all the points are showing right now. So I'm using uh, yeah, and also you can see at the end of the video, I'm showing that the total distance for one lap is 11.55 meter. So that's how I calculate the total distance of the first lap. Of course, it's not like a clean first lap. You have some
Right.
like a distance moved during the service phase and some other phase.
And how did you
So
get that 7 meter number? You just by trying, or how did you do that?
yeah, I'm just trying. I'm just roughly estimate that okay,
Right.
it's supposed to be 7
Mm-hmm.
because I've tried this so many times in simulation, and I was like, okay, this space is supposed to,
Right.
like 7 meters, but I don't know exact dimension of this space, but it's just a guess.
Yeah. No, I mean that's good enough.
Yeah,
All right. So at this point, it did the whole thing, right? It did the
yeah, it did
lap.
a whole thing.
It looked for the wall and found it. It did the one lap, and then it returned the list of odometries that is being uh, done by the action server, right?
Yeah, yeah,
Nice, nice, nice.
and the whole process takes about 5.5 meters minutes. Mhm.
Okay. So if everything is done, so it's just keep going on a loop. It's just going to do
Yeah,
it
yeah, it
forever.
just keep going. Yeah.
All right. Okay. Okay.
Yeah, I guess I can stop it here. I do have another test with a relatively harder starting position, but I don't think it will add any more value because it's
Yeah. Oh,
basically just
yeah. Let's. Why don't we do this? Why don't you just show us a little bit of your code and how you solved the sections, and then if we think it adds more, we can see that.
sure. Yeah. So let me first wall follow algorithm I was using. So on the left hand side in this plot, you're saying that you can see that I wrapped everything in a club in a class called the sub and the pub.
Mm-hmm.
So in this class, I have one publisher to get the information and publish the velocity information. So in this class, I also have this range mean function to calculate the mean the distance in the range, and I have this very convenient function to turn the robot and move the robot. So this x, z, and t basically describes the linear velocity and the rotational velocity and
And how
the
long you want to do it for?
how long I want it to do that action.
Okay.
Yeah, and this is and on the right hand side you can see this is the callback information that I have, callback function that I have. So the
For the subscriber, right? For
I'm
the
sorry.
scan subscriber. Yes, I can see that. Okay, yeah. It's
Yeah, yeah,
for
yeah.
the scanner.
Yeah, for the scanner. So you can see that this is how I make sure uh, the robot follows the wall. You can see I'm just simply using the conditional statements here
Yeah, yeah.
to make
That's what
sure
we need.
that I have all the conditions accounted for. So I'm also showing that uh, under what condition I would turn left or turn right or go straight forward. So if I have any obstacles, no obstacles detect, or there is obstacles on the left side or obstacles on the left and the right side, I will just turn right while moving forward. And if I have obstacle in the front or obstacle in front and left or obstacle in front and right or obstacle in front, left and right, I will just turn left.
And
Otherwise, I'll just move forward.
and by obstacle you mean the wall, right?
Yeah, the wall.
Okay.
So what do I mean by obstacle detected? So whether the obstacle is detected or not is dictated by this R max value. So if the minimum distance is less than 0.25, then I would say, okay, that's obstacle. If it's longer than 0.25, then I would just ignore it. So that's how I define obstacle detected. So yeah, so that's for the wall follow algorithm. And as for the service, yeah, because the wall found service is synchronous, we have to control the robot to find the nearest wall and adjust its orientation on the server before we can do something else. This is the definition of service. So we have no choice but do everything until we'll finish everything until the service says, okay, it's a go. Yeah. So yeah, in order to do so, I found a way to get the latest results from LiDAR by using this ROS topic wait for message. And also I use this publisher to periodically publish twist information to CMD val until some conditions are met. So this snippet of code actually is showing that how I adjust the orientation of the robot until I found the minimum distance is near the front of the it's right at the front of the robot. So as you can see here, this is a while loop, and in this while loop, I set up some like thresholds to make sure that the minimum distance is very, very close. It's very it's near the front of the robot.
Right.
Yeah. So and I also use ROS duration to send out the twist information periodically. So I'm just sending out information per every 0.1 second, so that the whole system does not overload by my information. And throughout this process, I'm also printing out some useful information telling me, okay, how everything is going. Like what's the minimum distance, current minimum distance is, and what is the current minimum distance at the front of the robot. Yeah, so that's the service. And then as for the action, it's relatively simpler than the service. Again, I'm using this wait for message to get the newest information from the topic odom. And I'm using the geometry message point to store the point information. So this one was used to store the three-dimensional information, but right now I'm just using the z variable in the information to store the orientation information. Yeah. So this is actually how. Yeah, I'm sorry.
No, go ahead.
Yeah. So yeah, this is how actually calculate the orientation value or theta. So I think the odometry odometry information was using the quaternion to record the orientation of the robot. So this is the formula that I found online to calculate the theta value. And once I record the point, I just push back the newest point at the end of the list of the odom information. This is an array of the point here that I'm recording, and I'm also recording the total length of the information array so that I can use it later. So the second part is just how I decide whether the first lap is finished. Like I already mentioned, the first lap is finished when the total distance is larger than the 7 meter, and then the latest coordinate and the coordinate recorded previously have a distance less than 0.05 meter. So it's actually pretty small distance. So if both the conditions are satisfied, then I will just call it a full first lap.
Right. And then at that moment, return.
At that moment, everything is down, and I would just keep the robot running and follow the wall. So that's the whole story of my project.
Well, very, very nicely presented. Very nice. Do you mind? You're done, right?
Yeah, I'm done. Yeah,
Or do you mind stop sharing your screen so we can just go over it?
sure. Yeah. Should I stop sharing now?
Yeah, yeah, you can stop sharing now.
Yeah.
All right. Well, let me see. Well, really nice project, CJ. Congratulations. Um, let me say that I have a couple of questions, so let me ask you those.
Mm-hmm.
So you first of all, I thought it was really interesting that that formula you showed me for changing the quaternion to to roll
To
pitch yaw
theta.
to
Yeah.
so I didn't know you could just use the z component uh, to change it to a theta like quaternion to Euler because usually there's also a function that's already made that you have
Mm-hmm.
to give all of the elements of the quaternion and then it
Mm-hmm.
just returns the function just returns the roll pitch yaw and then you can take the yaw. So it's nice to see that there's another way of taking
Yeah.
that value.
Yeah. I used to work with the quaternion before, so that's why I
Oh, I
get to.
see, I see. So that's really interesting. And I also wanted to ask you so the robot starts looking for the wall when you launch the program. And so what would happen if there is an obstacle, not the wall, but like one of the obstacles that are in the middle? So what would
Mm-hmm.
happen in your program if you launch the main program nearer to one of those obstacles? Would it just think that's the wall and go to it?
Oh, yeah. I actually have another test with it's a starting point near one of those obstacles at the center.
And
Uh,
what happens in that case?
you want to see? I actually can show you the
Yeah,
video.
let's see it. Let's see it.
Yeah.
So you can share your screen again.
Yeah, sure. Yeah, I just want to. I did this just because I want to see how robust my algorithm is.
Mm-hmm.
Um, that's just how I usually do things. Can you see my screen
Yeah,
now?
I can see it.
Yeah. So you can see the starting point right now is
It's
very near.
closer. Yeah, yeah. That's
Yeah,
what that was
very,
my
very.
question. What happens if this happens? Yeah, yeah.
Yeah. So it's very close to one of this. Actually, it's too close to two of those obstacles,
Yeah.
and this time it takes way longer time to find the best way out. But yeah, the point is it is still found a way out of there, but in a very interesting and unexpected way. You will see why I say that.
Mm-hmm.
So right now it's just doing the normal thing, and then you can see it's just keep rotating.
Right, because this
Um,
moment it would still look at the minimum values and it would be the
yeah,
obstacles.
but the thing is, the front is actually very near the edge of the obstacle.
Uh-huh.
So if you just rotate a little bit, the the distance will be changing very in by a very large amount because you see that it's not just like facing the obstacle. If you just rotate a little bit, you will have one of the range
Yeah, yeah. Yeah, I
shoots
see. I see. It'll
towards the
change
wall
that
at this
drastically
time.
because it's looking at an obstacle and then it's looking at the
Yeah,
wall behind it.
yeah. So it confused the robot a little bit at the very beginning. Like so you see you have some crazy number like minimum distance is mid distance is infinity. It's just because it's too close to
Yeah.
the wall, the obstacle. Um, and now you see that okay, it feels like okay, the robot found the right position right now. Now you have to move towards the the obstacle that is nearest the robot. But now see what is happening. The current minimum state is still infinity. It's just because
I
yeah
see.
it's just because that obstacle is too close to the robot. So
Yeah.
you still need to adjust the orientation of the robot.
So it's
You
still
see
gonna
that
rotate.
because it's the infinity, and it actually moves towards
Yeah, I see.
the obstacle, and actually makes the obstacle rotated a little bit,
Wow.
so
So
that
if
he
it
can.
does it get out
Yeah,
of this situation? Because that would be
yeah,
impressive.
yeah. It get out of the information situation like this. So you see that it's at the beginning. I believe that he think the robot thought that this obstacle is the nearest one.
Hmm.
But since now, when it crashes it rotates the obstacle a little bit. Now it thinks that okay, this one is the nearest one. So the robot moves towards this one instead of this one.
Okay.
Yeah.
And then eventually we'll find the wall in this video.
Yes.
Yeah.
Yes.
Oh, that's
Yeah,
crazy.
he found like.
So at this moment though, why doesn't it think that the closest obstacle is the one to like not the one in
Yeah,
front,
because
but
I think this is something related to the leader that we have on this robot. Because if you have a super close distance,
yeah,
it
but
will
it's
give
not.
you.
It's very very close. So that's the
Yeah,
most lighter. Yeah, it gets an infinity.
yeah.
That's really interesting. That's really interesting.
Mhm.
Just leave it playing, just to see what let's see what happens.
Yeah, sure.
And
It's now rotating right now. Oh, okay.
so yeah, there's a bunch of ways that people have tackled this problem to recognize
Mhm.
basically between the wall and the um, obstacle. It's not explicitly required in the project, but it's always
Mhm.
nice to see that people like you go a little bit above and beyond to make sure this happens. And a lot of two people have done a certain kind of filter, so the wall is
Mhm.
following a pattern, so there's no
Mhm.
big jumps in the values of the distances. It's always increasing or
Oh yeah.
decreasing smoothly. And if there's a big jump, you know that all right, that's something else. So
Yeah, I
there's a
did that. Yeah, I did that also.
uh-huh.
My first version of this project. And also I use I actually calculate the average distance in the range array to make
Right.
sure that I'm not just using one of the elements. I'm using like maybe 10 of the elements
Yeah,
to
that's another way
calculate
to
the average distance from the robot to the obstacle at the middle.
that's good.
Yeah.
um all right, so what
So right
else?
now I think it's still rotating. Don't embarrass me, please.
That's all right. If it doesn't work, doesn't work, doesn't matter.
Yeah, we can.
Put it all the way by the end because we're almost out of time here. So let's see what happens.
Yeah.
Like,
So at this point, I think yeah, it found it. It found it. It found the wall. At this point, now it
now
moves
it's gonna
away
go
from
towards it.
yeah, towards it. Yeah, towards the wall.
Nice. That's a really nice behavior, and it's gonna start okay, and it's gonna line
Yeah,
up and start doing it. Nice.
do it a wall follow again. So just like that.
All right. Well, you can stop sharing your screen now. Thank you.
Sure. Yeah.
All right. So, I mean, congratulations. This was really nicely done and presented. I saw that you did a nice way of organizing your code into classes, which probably made things easier as it goes along, um, and that way you can expand it. So, congratulations. I really like that. And
Mm-hmm.
just one more question that I kept thinking about that 7 meter number. So
Uh-huh.
if you were to think about a way to um, not do this hard coded, let's say, do you have any ideas on how you would detect that a full lab has been completed?
Yeah. So I probably was just I tried this first, but maybe this is just something I did wrong in my code. So my first idea is I would just first let it run until um, the latest uh, the latest recorded coordinates is very close to one of the points recorded previously, and at the same time the orientation is like at the opposite direction.
Okay.
Yeah. So So in that way, I think maybe I can call it a full lab. But yeah, but it's kind of hard to. I think this kind of this way is not robust, because if you think about if you have a starting point that is very close to the obstacle, like I just showed in my second video, then it will just run just make turns near the obstacle, and always like make some like small changes near those obstacles. It might not be a very accurate way to call it a full lap, but that's just my first idea.
Right. Yeah.
To avoid hard coding. Yeah.
That's a good idea. Another way, but I mean, if you haven't taken another course and if to do it is using the TFs, right? So I don't know if you know a lot about TFs.
Yeah,
would be to
I'm learning it
publish-
right now.
Yeah.
But,
So there you go. So then maybe for your next project you can do it. So to when you start, you publish a transform there, and then it's gonna go away from it at the beginning, and then once it's starting getting close, you can kind of detect that. But that other way, it seems interesting and promising. But anyway, say Jay. So thank you very much for presenting your project, and for everyone else that is watching, you can do this as well. If you take our course and want to obtain our certificate, come and present what you've learned, and hopefully you'll do a good job here like CJ. So thank you very very much.
Thank you. This is very nice class. Hope everyone enjoy it and learn useful things from it. I did, and I hope all of you guys did as well.
I'm glad to hear that. So, anyways, that's it for us, guys. So, see you next time for our next presentation. So, bye-bye.
Bye.
Okay, I have ended the stream. Nice.